3. So today we're going to talk about conduction, convection and radiation. So do you guys know what is the difference conduction, convection and radiation? You guys don't know? Let's talk more about it.
Now, let's talk about radiation. Radiation is an energy emitted by matter in the form of electromagnetic wave. The result changes in the electronic configurations either in the atom or the molecules. Now, we have the thermal radiation. Thermal radiation is the form of radiation emitted by the bodies because of their temperature. There are types of the thermal radiations which are X-rays, microwave and also television wave. Now these examples are not related by the temperature. Now you may wonder, is the transfer the fastest? And yes, the answer is energy transmitted by the radiation is the fastest at the speed of light. And there are three types which are solid, liquid and also gas emit. Thus, a black body is a perfect emitter and absorber of radiation. The examples of a black body are radiation heaters, sun and also night vision equipment. Lastly, we have the Stephen-Boltzmann law, and here is the equation. Stephen-Boltzmann law is a statement that the total radiant heat power emitted from a surface is proportional to the fourth power of its absolute temperature. Radiation is widely used in the industry and it has many applications. For example, it is widely used in the medicine field as an X-ray, archaeology, which is used in carbon dating, and lastly we have geology, which are used in mining. That's all from me. Thank you. So I'm gonna explain what is convection. Convection is the mode of energy transfer between a solid surface and the adjacent liquid or the gas that is in motion, and it involves the combined effects of conduction and fluid motion. So the heat transfer through the fluid layer will be by convection and conduction. Convection when the fluid involves some motion, and conduction when the fluid layer is motionless. So I'm gonna show you about the example of convection and how it works.
Here we have some chickpeas in a beaker of water and we're going to bring it to the boil. By heating it up, we can follow the convection currents in the beaker or the water by watching the movements of the chickpeas. The temperature of the bottom of the beaker, the bottom of the water, is much warmer than the water in the top region of the beaker. The particles at the bottom, they gain this extra energy, this extra kinetic energy, and so the particles move further apart. When the particles move further apart, you create a low pressure zone, or a lower density. So with the water, it becomes less dense at the bottom because it's warmer, and so we know that things that are less dense will tend to rise to the surface. When it rises to the surface, it carries those chickpeas up with it to kind of demonstrate to us what is happening. So this picture here is from Wikipedia, some illustrators called Orion and Construct, 2007. They're basically illustrating the same thing that we saw in the chickpea beaker. The heat is being applied at the bottom of the beaker, and so everything that is closest to that side of the beaker is going to be very much warmer than the top. When the chickpeas and the hot water rises to the top because it's less dense, it is then exposed to the cooler atmosphere because the air around at the top is much cooler than the air below, which was made as a hot Bunsen burner. So that means that it can give away some of that heat energy to the cooler air particles above the surface of the water. When it does this, it loses its heat energy. It loses this movement or this kinetic energy that each particle has, and so they kind of come closer together because they're pushing each other apart less. So now that they're more dense, they then sink down to the bottom of the beaker and they go the process all over again. I hope this helps.
This is the equation of the rate of convection heat transfer. So there are two types of convection, which is free or natural convection and forced convection. Free convection would be associated with vertical plate and cylinder, horizontal plate and cylinder, and sphere. And for the forced convection, it is flat plate, cylinder, and sphere. So free natural convection is where any fluid motion occurs by natural, and it is often not noticeable because of the low velocity involved. Forced convection has two categories, which is external forced convection and internal forced convection. External forced convection is when parallel flow over flat plates, cross flow over cylinder and sphere, and flow across tube banks. As for the internal force convection is laminar, transition and tubular flow in tubes. There are 4 dimensionless numbers in free convection, which are Rayleigh number, Grashof number, Prandtl number and Nusselt number. As for the force convection, it is Reynolds number, Nusselt number and Prandtl number. So here is the equation of the dimensionless number. Moving on to the next part, there are two types of film and overall heat transfer coefficient. The first one is U for a plate and the second one is U for tube or cylinder. U for a plate is a common practice to relate the total rate of heat transfer Q to the cross-sectional area for heat transfer A and the overall heat transfer coefficient U. Therefore, Q can also be defined as this. In U for tube or cylinder, there are 3 processes involved, which are heat transfer coefficient, cross-sectional area for heat transfer, and temperature difference. Here is the equation for U for tube or cylinder. Moving on to the optimal insulation thickness, there is thermal insulation. Thermal insulation are material or combination of material to provide resistance to heat flow. The temperature difference is the driving force for heat flow, and the greater the temperature difference, the larger the rate of heat transfer. Thermal insulations serve as such barriers, and they play a major role in the design and manufacture of all energy efficient device or system. There are few examples of thermal insulation. The first one is heat generated in furnace by burning coal. Insulation reduces the amount of heat loss. The second one is we minimize heat loss from our body by wearing coat or a sweater. And the last one is the insulation layers in the wall of a refrigerator reduce the amount of heat flow into refrigerator. The R value of insulation is the thermal resistance of the material per unit surface area. This is the equation for the R value of insulation. Natural convections play an important role in many industrial applications, such as power generation, food processing, and electronic cooling. For the electronic cooling, convection cooling involves the transfer of heat from a car into the ambient air using airflow. There are 2 basic types of convection cooling, one that relies on natural airflow and one that requires forced airflow via fans and blowers. Food processing industry also use convection as a method of heat transfer. There are 2 types of method used in food industry, which is convective drying and convection cooking. Convective drying is a common method for drying fruits and vegetables, and convection cooking is used the movement of molecules in the fluid to transfer heat. The examples of food cooked by convection include rice, pasta, and cake.
I will explain about heat conduction. What is heat conduction? Heat conduction is the transfer of heat energy through a solid material or between objects in direct physical contact without the movement of the material itself. It occurs due to the vibrations and conditions of atoms, molecules, or free electrons within the material, transferring energy from regions of higher temperature to regions of lower temperature. This process abides by the Fourier's law. This is the equation of Fourier's law. So how does it work? Conduction only works when there is a direct contact between objects or within a material. Heat always moves from the hotter object or area to the cooler one. This is because energy naturally spreads out to the balanced temperature. Well, you may wonder, how does this apply in our daily life? So, I will insert with the video.
Thermal energy moves in 3 main ways: conduction, convection, and radiation. The movement of heat within a solid object is called conduction. Conduction also occurs when objects are touching. Look at the kettle on the stove. Heat from the flame moves through the metal of the kettle to the water in contact with it inside. This is an example of heat conduction. Butter melting on a fry pan is another example of heat conduction. The air in a hot air balloon is heated by the burner and rises up inside the balloon. As the hot air rises, the cooler air falls and creates a current within the balloon. The convection current causes thermal energy in the air to spread through the balloon. The warmth you feel when you place your hands near an electric heater or a campfire are examples of heat in the form of radiation. We can observe conduction, convection, and radiation when water in a kettle is heated. Thermal energy moves through the metal to the water by conduction. Thermal energy moves around the water through convection. And finally, the heat leaves the kettle and is transferred to its surroundings by radiation. I hope you had fun learning about heat. See you next time.